Welcome, everyone, to another deep dive. Today, we're tackling a truly massive question. What is the shape of the universe? We'll be looking at how our understanding has evolved, starting with those early observations of the night sky and then going, well, kind of cosmic.
Yeah, it's a journey that's really changed how we view the universe. For a long time, the only way we thought about space was through Euclidean geometry. But, when non-Euclidean geometry came along, well, it opened up whole new dimensions.
I think a lot of people hear non-Euclidean geometry and their eyes kind of glaze over. Can you give an example, something people can actually picture to show how it relates to the universe's shape?
Sure. Let's say you draw a triangle on a flat piece of paper. All the angles add up to 180 degrees, right? That's good old Euclidean geometry. But now imagine drawing that same triangle on a sphere, like a basketball. Suddenly, those angles add up to more than 180 degrees. That's non-Euclidean geometry at work, and it's how we begin to grasp the idea that space itself can be curved.
Okay, I can see that. A triangle on a basketball. It makes sense. So how does Einstein and his famous theory of general relativity come into this picture?
Einstein's theory was a total game changer. Before him, gravity was seen as just a force between objects. But Einstein said, nope. Gravity is actually the curvature of space-time caused by mass and energy, that curvature. That's what we feel as gravity.
So we're not just pulled down by the Earth, but we're moving along the curves it makes in space-time. That's wild. And I can't believe it's been almost a century since Hubble discovered the universe is expanding. That must have thrown another wrench into everything, right?
Absolutely. Hubble showed us that galaxies are moving away from us, and the further away a galaxy is, the faster it's zooming away. Now put that together with Einstein's theories, and suddenly the universe's shape isn't so simple anymore.
So, just because when we look up, the night sky seems flat, doesn't mean the whole universe is right.
You got it. We could be seeing a teeny flat bit of something much bigger and much more curved. It's like, think of an ant on a balloon. To the ant, the balloon seems flat. But zoom out and you see, nope, it's curved. It's the same with the universe, just, well, way bigger.
That makes sense. So how in the world do scientists even try to figure out the shape of something so vast?
Well, one way is to look at the cosmic microwave background radiation. It's the afterglow of the Big Bang itself, like a baby picture of the universe. And in that picture, there are little patterns that can tell us about the universe's early structure and its geometry.
It's amazing we can even see that far back. And I know the density of the universe is important too, right? Something about a density parameter.
Right, that's omega. If omega is 1, that means the universe is at a specific density, and that means it's flat. If omega is bigger than 1, we've got a positively curved universe, like that sphere. And less than 1, that's negative curvature, like a saddle shape.
So where do we stand? What's omega telling us right now?
Well, the measurements we have put omega incredibly close to 1. Which means at least the part of the universe we can see seems pretty darn flat.
Wow. So we're basically living on a cosmic flat plane. Does that make things simpler?
Not necessarily. Remember, we're only talking about the observable universe. And this is where things get even trickier. Because now we have to think about the global topology of the universe.
Topology, yeah. It adds another whole layer to this.
I'm already feeling a little lost, to be honest. Topology, is that even harder than the geometry stuff?
Don't worry, it's not that bad. Think of it like this. Curvature, that's about the shape of space right here, locally. But topology, that's about the overall shape, how the whole thing connects to itself.
Okay, I think I need a picture in my head for this one, like an actual example.
All right. Imagine a flat sheet of paper. Totally flat, zero curvature, we agree. But you could roll that sheet into a cylinder, right? And if you're just on the surface, it still feels flat. You can even connect the ends, make a donut shape, a torus. It's still locally flat. That's the difference. Geometry versus topology. Wow, yeah, I get it now. So even if we knew for sure the universe was flat, like what we can see of it, the whole thing could be, well, any number of crazy shapes.
Exactly. And that's what makes this so exciting and so tough to figure out.
So we've got curvature, density, and now this topology thing. But haven't scientists come up with like actual models for what the universe might look like overall, even with all this uncertainty?
Oh, yeah, definitely. And some of them are pretty wild.
I remember you mentioned the Poincare dodecahedral space earlier, the one that's like a soccer ball. Could you unpack that a bit more?
So in that model, the universe is finite, meaning it has an end, and it's made up of these 12 pentagonal faces. Light would travel through it in these super complex paths. And the cool part is, If that's how it is, we might be able to see these repeating patterns in the cosmic background radiation because of the way it's all connected.
So if they found those patterns, it'd be like, uh-huh,
Hmm.
soccer ball universe, confirmed.
It would be huge, for sure. But finding them is really, really hard. It's something scientists are actively working on, though.
Okay, so all this is super interesting. But honestly, why should anyone care about the shape of the universe? Is it just like a brain puzzle for scientists, or does it actually affect anything?
Great question. It's not just some abstract thing. Figuring out the shape has real consequences. It affects how we understand how the universe evolved, what's going to happen to it in the far, far future, and even the basic laws of physics themselves.
Wait, are you saying the shape of the universe is, like, tied to its destiny?
That's right. For example, think about a closed universe, one that's curved in like a sphere. Eventually, that expansion would stop and everything would start collapsing back in, a big crunch. But an open universe, curved outwards, the expansion just goes on forever. And a flat one, it slows down but never quite stops. Totally different endings.
So we could go out with a bang, a slow fade, or
Yeah.
something in between. That's a lot riding on the shape.
It really is. And it all connects to some of the craziest ideas in physics, too. Stuff like string theory and the idea that there might be multiple universes out there.
Hold on, multiple universes,
Yeah.
like more than just ours.
Yep. Some versions of string theory, that's the one trying to unify all the forces of nature, they say our universe might be just one of these things called brains. Imagine them like sheets or membranes floating in some higher dimensional space.
So, like, our whole universe is on a sheet. And there are other sheets out there with other universes on them. My brain hurts a little.
It's pretty mind-blowing. And the way those brains interact, well, that could affect the shape of our universe, how it changes over time.
We're talking about universes bumping into each other, shaping each other. This is getting hard to even picture.
It's pushing the limits of what we can imagine, for sure. And remember how you said earlier that even future experiments might not give us a definite answer?
Yeah, I remember. It makes it all feel kind of pointless, like we're never going to know for sure.
Oh, not at all. In science, even if we don't find the answer, the searching is what matters. We learn so much along the way. Even if we can't perfectly measure the shape, we're always finding new things. It's the journey of discovery that's the real point.
Okay, I like that way of looking at it. So what are some things you hope people take away from this deep dive? Like, what's the most important stuff?
I think the biggest thing is just appreciating how complex and weird the universe really is. We've come a long way from thinking it was this static, never-changing thing. And Einstein, Hubble, all that, it showed us just how dynamic it really is.
Yeah, and we've seen how density, topology, all these things play a part in shaping the universe, literally.
Right. And even with all that, there's still so much more to discover. That's part of what makes studying the universe so captivating, you know?
It's like we're explorers mapping out a new world. We might not have all the pieces of the map, but that's what makes it an adventure.
Exactly that. Even though it's so hard to wrap our heads around some of this stuff, the fact that we're even trying to figure out the shape of the universe, well, it says a lot about us humans. We're curious. We want to understand where we fit in the big picture.
Well said. This whole deep dive has been mind-blowing for sure. But before we get totally lost in space, so to speak, we should probably wrap things up for today. But I do want to leave our listeners with something to think about, something really intriguing.
You know, that idea of a finite universe, like the Poincaré one, like a soccer ball, there's something really trippy about that, even if it is that shape.
Okay, lay it on me. What is it?
Imagine you're flying through this dodecahedral universe in a straight line. What happens when you hit one of the faces, the edges of the soccer ball?
Well, I mean, normally you'd run into a wall, right? Like, that would be the end, the edge of the universe.
Not so fast. Remember, it's finite closed. There's no edge like we usually think of one.
Well, hold on. So I just, like, go through the wall, pop out the other side?
Maybe. Or maybe you seamlessly transition to another face of the dodecahedron. Like in a video game, you go off one side of the screen, you appear on the other.
So even though it's finite, you could travel forever, just going around and around.
That's the idea. And it starts to mess with how we think about space and time and reality itself.
It's like, even if there are boundaries, they might not be what we expect. Maybe there are these hidden connections, things we can't even picture yet.
And those are the questions that'll probably keep scientists busy for a long, long time.
Makes you feel kind of small, doesn't it? Thinking about all that, well, this whole deep dive has been incredible. Curvature, density, topology, multiverses. We've gone all over the place.
It's been fun talking about it all with you. Hopefully everyone listening feels a little more awe about the universe and maybe wants to learn even more.
Absolutely. And the biggest lesson here, even with all the amazing things we've figured out about the universe, there's still so much more out there waiting to be discovered. That's what makes it all so exciting.
Couldn't have said it better myself.
So to everyone listening, keep looking up, keep asking those big questions, and never stop exploring the cosmos. Thanks for joining us for this deep dive into the shape of the universe. Until next time, keep wondering.
Keep wondering.